University of London, Department of Mathematics, and he's going to talk about market price of risks, facts, and fallacies. Thank you very much.
Thank you, Carol. And thank you, Georgia, and the other organizers for the invitation to come to this nice meeting. What I have to say today is based on joint work with Dorje Brody and David Meyer, who are both at Brunel. Let me begin by saying a few words about what we mean by models and what we mean by families of models. Now, if we went around this room and asked everyone one by one what they meant by a model in finance, I'm sure you'd get many different opinions. I'll give you at least one definition, and then you can reflect on how this might agree with the way you would put it if you asked the question yourself. So we'll take the view that the pricing kernel, or state price density, or stochastic discount factor is or should always be involved in the specification of a model. So the general idea is that we fix a filtered probability space. We'll always work with the physical measure. It'll be understood that we have some notion of what we mean by the physical measure. To keep matters simple, we'll consider the case of a single asset when there are no dividends paid over the relevant time horizon. If there are dividends, if there are many assets, well, things are slightly more complicated, but not fundamentally more complicated. So by a model, we mean a pair of processes, pi and s. Pi is the pricing kernel, and S is the asset price process. And then we require that the product should be a martingale. Now, there are situations where you might want to relax this condition of martingale and so on and so forth, but in almost all models of a practical use in finance, one imposes a martingale condition. So that's what we mean by a model. You can generalize in your own mind to the case where there are several assets and so on. Now, what do we mean by a family of models? Well, we mean, at least in this definition, a parametric family of models. So this will be a collection of models labeled by the elements of some index set. So let me give one or two examples. So by the geometric Brownian motion model, which is widely used in finance and forms the basis of the Black-Scholes theory and so forth. So we mean a pair of processes given in the form indicated. So pi is a sort of discount factor times an exponential martingale, where the relevant parameter lambda is what we call the market price of risk. Note that there's a minus sign. And then the asset price has several different ingredients. There's initial price, and then there's a geometric Brownian motion with a parameter sigma, which we call the volatility. And then the rate of return on the asset, well, there's an interest rate, and then there's an excess rate of return, which is given by the product of market price of risk and the volatility, and we take these various parameters to be constants. W is a Brownian motion. Then you can easily check that if we take the product, then you get a martingale. And again, it's an exponential martingale, and this time with a volatility given by sigma minus lambda. So that's an example of a model. And then by an example of a parametric family of models, well, we take the geometric Brownian models, Brownian motion models, and we fix the initial price and the interest rate and the volatility, but we allow the market price of risk parameter lambda to vary over its admissible values. And so that gives us one parameter family of models labeled by lambda. So now let's look at the payoff of some derivative. And we'll keep things very simple. So the derivative, well, we have a fixed maturity date, capital T, and then the payoff is given by some function, and we require f to have suitably nice properties. And we have some function of s at the maturity date, and that gives the payoff. And then the price of the derivative is given by the expectation. This is always under p measure of the product of the pricing kernel and the payoff. Now, in this case, we're looking at a parametric family of models, so this gives us a parametric family of payoffs and correspondingly a parametric family of prices that result when we look at the different values of lambda. Now, we know from the experience in calculations and just our knowledge of how the Black-Scholes theory and so forth works, that in this situation, for each member of the parametric family, in fact, you get the same value for the option price, for the derivative price. So a priori, H naught depends on lambda, but in fact, when you do the calculation, you find that it doesn't. So this gives us a sort of slightly clearer formulation of what is sometimes meant by the loose statement that the option price, in this case, doesn't depend on the market price of risk. We introduce a parametric family of models and then show that they all give the same results. Now, let me look in a little more detail in an example where we know that this is the case. And then I'll turn to some examples where it's not necessarily the case. Well, this will be very familiar. I'll run through the derivation of the Black-Scholes formula, but I won't do it via the usual arguments involving hedging and risk-neutral measure and portfolios and so forth, but we'll just do a direct valuation using the pricing kernel. So the payoff function is familiar, and we know what the result is in terms of the Black-Scholes formula, which doesn't depend on lambda, even though you can make any choice for lambda in the parametric family. So the argument proceeds as follows. S is the given random variable. Here's the expression for the pricing kernel. If you put those both into the valuation formula, then we have this expression for H naught. It depends detail by detail on lambda. And then we can run through the valuation of this expectation. Well, the max function achieves its maximum value at a certain point. So if we set z equal to w minus the square root of t, then we know the max function is positive if this inequality is satisfied. Lambda is still involved. So we adjust the range of integration to reflect that. And then we make a change of variables. And then after we make the change of variables, then miraculously lambda drops out. So we obtain an integral. We can do the integral by standard techniques. And then that gives the Black-Scholes formula. So we see as expected that H naught is independent of the choice of the market price of risk. Or to put it another way, if we look at these various models in the family of models parameterized by lambda, then each model gives the same value for the call price. Well, there's nothing at all controversial about this. This is a sort of standard or well-known result in the literature. But here we've phrased it with the idea that we have a family of models, all of which give the same price. And this result, of course, is well known in the Black-Scholes theory, and it was one of the results that was responsible for the success of the theory because it showed that a trader could value call options without necessarily having to take a sharp view on the rate of return offered by the underlying stock. And it's historically kind of interesting because Samuelson, just a few years earlier, before Black-Scholes, had written a lengthy paper called Rational Theory of Warrant Pricing. It turned out actually to be an irrational theory of warrant pricing. But he essentially got the Black-Scholes formula, except for one thing. He took the expected discounted payoff of the option, leaving the actual rate of return of the stock in the formula rather than replacing it by the interest rate. And this small detail was eventually, in effect, explained by Black-Scholes and led to what we regard as the sort of modern theory of mathematical finance. Now, it would be a mistake to conclude on the basis of the Black-Scholes example that option prices in more general models don't depend on the market price of risk. If you take such a family of models, sometimes they do and sometimes they don't. So to give an example in more detail, I'll look at a stochastic volatility model. Now, it turns out that it's not altogether easy to construct models that are explicit that you can really get your hands on, where the option price depends on the market price of risk. One can see easily enough in principle that ought to be the case, but it's one thing to discuss principles, another thing to actually get your hands on it. So we'll try to look at an example where we see it explicitly. So we'll look at a stochastic model, volatility model. We'll keep the same family of pricing kernels for different values of lambda, but we'll let sigma be a stochastic volatility. Now in this case, we're not going to introduce multiple Brownian motions and stochastic volatility in the style of Hughston and so forth. We'll keep it very simple so that sigma itself is understood to be an adapted process, adapted to the filtration of the single Brownian motion that's driving the model. And we'll assume that the sigma has this square integrable property. So again, that simplifies the model further. And then we obtain, in this way, a parametric family of models for the share price. So we've got lambda appearing explicitly in the rate of return on the share. So now let H be the price of a derivative, where again we have a payout given by F, of the terminal value of the asset. To simplify the matters further, we'll assume that F is smooth. So we'll eliminate the kind of corner that one has for a call option. Then for the price of the option, well, we take the pricing kernel times the function, we form the expectation, and after a little bit of rearrangement, we can write this expectation as E star of F of S, where E star is obtained by changing measure using the martingale part of the pricing kernel. And then we can combine together the W and the lambda T in order to create a W star in the expression for the price. And now we want to value the option. So what we'll do is we'll take a perturbative approach. So we'll consider the case where the stochastic volatility is of the form beta times gamma, where gamma is an adapted process, and we're going to make beta small eventually. The idea is that if we can look at options that have payoffs that will differ just slightly from the payoff in the absence of volatility, and if we can show that that depends on the market price of risk, then that's sufficient to establish that in general we have this dependence. So we can write the asset price in this slightly abbreviated form. We have S naught times e to the RT, e to the beta x minus 1/2 beta squared y, where x is given by the integral of gamma with respect to W star, and y is integral of gamma squared. And to simplify the notation, I'll write S bar for the forward price, S naught e to the RT. And for our perturbation calculation, we need some derivatives. So it turns out we need to work out the second order, not just the first order. So we'll take the first derivative of S with respect to beta, so that's x minus y times S. Remember, x and y are these random variables defined above. And gamma itself is a process, so it's a random process. Then we can form the second derivative. That involves x minus beta y squared times S minus ys. And then we can look at the perturbation associated with the payoff function. So we use the chain rule. I write this out because it's, although it's straightforward, it's not altogether trivial. So if we take the derivative of f with respect to the volatility parameter beta, then we get ds by d beta times f dash. F dash means the derivative of f with respect to its argument s. And then plugging in the previous result, we get x minus beta y times s times f dash. And then finally, we can take the second derivative, and it gives rise to this slightly complicated expression involving f double dash and f dash. So assuming that f is smooth, then we can expand f in a power series around beta equals 0. So beta equals 0 involves the payoff of the option and the stock in the case when there's no volatility. So we just have the payoff at the forward price. And then we have a first term and a second term and higher order terms. So putting all that together, now we have a formula. F of S of beta, so that's the payoff function as a function of the share price and the volatility parameter beta. So the first order in beta, we get X times the forward price times F dash of the forward price. And then the second order, we get 1/2 beta squared times X squared forward price squared F double dash at the forward price plus another term, X squared minus Y. And you'll notice that the randomness is in the entirely in the X squared here and the X squared minus Y. So now we're in a position to take expectations. But this first term involving X, that expectation vanishes. And the second term, the term involving X squared minus Y vanishes. So if I go back, you see this term here involving X vanishes when you take expectations. So that shows you that the term that's first order in beta just drops out. And if we look at the second order term, well, there's a term involving X squared minus Y, and that vanishes when you take expectations, since Y is essentially the quadratic variation of X. So we're just left with the term involving X squared. So this gives us a formula that to second order in beta, the option price is given by the discount factor times the payoff at the forward price plus 1/2 beta squared discount factor forward price squared F double dash valued at the forward price times this expectation. So that's integral of expectation of gamma squared at ds. So the whole problem boils down to the valuation of this integral. So far we haven't actually said what the stochastic volatility model is going to be. So again, it'll suffice just to consider a single example, and we'll look at a kind of linear Brownian quadratic or stochastic volatility. So gamma is of the form A plus B times W, where A and B are constants. Now, there's no reason to suppose that this is a realistic model for stochastic volatility. Maybe an Ornstein-Uhlenbeck type process would be better. But the idea here isn't to construct a realistic example. The idea is to construct any example, because then that will provide a counterexample to the idea that the asset, that the derivative price should be independent of the market price of risk. So that's going to be our model for stochastic volatility. W is the p-Brownian motion. Now, you can express W in terms of the q-Brownian motion W star. So you rearrange, and you see gamma depends on lambda then. So we insert this expression for gamma into the expectation and the integral. So this is the term that provides the price. And you can do the calculation explicitly. It's a simple exercise in Ito-type calculus and so forth. And you find that what you get is a cubic polynomial in T involving the constants A and B. So then to first order, you can look at various examples. So let's look at the case B equals 0. So that's the case when we simply have a constant A. So this reduces to the simplest sort of example that you can get with constant volatility. And there you find that H naught is equal to the value of F at the forward price of the underlying asset, and then you get a perturbed term. So this is the term that you would get if you just took the ordinary Black-Scholes formula and took a perturbation for a very small volatility, and this would be the sort of second order effect that you would get in the price, and of course it doesn't depend on lambda. But on the other hand, suppose that A is 0 but B is non-zero, and you do the calculation, then you find that the option price is given by the discounted value of the forward price plus this term 1/4 constant B times beta squared T squared, and the key point is that the market price of risk enters. So we can rearrange that slightly and express this as a kind of a correction term. So the price of the option is equal to the price of the option you would get if you set the market price equal to 0, plus a correction term, which is quadratic in lambda and goes is cubic in time. Or more generally, if a is not equal to 0, then here's an explicit form for the correction term. So this is a simple example of a calculation that you can do to show that for stochastic volatility models, in general, the option price that you get depends on the market price of risk. Now, that doesn't show that all stochastic volatility models lead to option prices that depend on the market price of risk, but this shows that in general they do. Now let me come to another example. This will be an example coming from interest rate theory. And we'll look at the rational log normal model. The reason why we look at this model is not because we necessarily think that it's a realistic model, but again because one can do the calculations explicitly and one can illustrate certain principles in a way that is direct rather than having to kind of infer the results in a roundabout way. So here's the rational log normal model. We let A and B be positive deterministic decreasing functions, and we let M be a standard extended geometric Brownian motion where sigma is deterministic. And then our model for the pricing kernel will be A plus B times M. Remember, A and B are deterministic, so you can then work out the discount bond price. And you get A at big T plus B at big T times the martingale M divided by A at little t. It does work. Okay. Can you hear better now? Okay. Okay. It's not my fault. Okay. I hope that's better. So you can work out what the bond prices are. And you can also work out what the short rate and the market price of risk are. So if you take the derivative, oh, that's better, I think. If you take the derivative of pi, then you get minus r is the drift and minus lambda is the volatility. And just by using Ito calculus, then you find that the short rate is given by this bilinear expression in the martingale M. And the market price of risk is also a bilinear expression in the market in the martingale M. And in fact, in this model, the short rate can be used as a state variable. This isn't immediately obvious, but it's true because you can invert this relation between M and R, and you can express M in terms of R. So M can be expressed as a bilinear function of the short rate, or a rational function of the short rate. So this is why we call these rational models. And then if you insert this expression for M back into the formula for the market price of risk, then you're left with an expression for the market price of risk as a function of the short rate and deterministic coefficients. And then it turns out sort of miraculously in this particular model that the market price of risk is actually linear in the interest rate. So what you can see is that in this particular model, it's a parametric model for interest rates, the market price of risk is given by a linear function of the short rate with deterministic coefficients made up out of the A's and the B's. So what this implies is that if somehow we can calibrate A and B and sigma to cross-sectional market data at time 0, then we can determine the market price of risk at any value of t if we're given the short rate. Now, we'll regard the short rate as being observable in the market, and so this implies that the market price of risk is observable in the market at any time. So that brings us back to the question, well, can we calibrate the model to cross-sectional data? It's not immediately obvious, but here's an argument that shows how it can be done. So for our data, we'll consider digital put options on discount bonds. So we'll use the following notation. We'll let little t be the option maturity and big T be the bond maturity. And then we pick a strike, and then the payoff is going to be the indicator function for the discount bond being less than the strike. So if we put that in the valuation formula, remember E again is the physical measure. So we have price in kernel times the indicator function, and we rearrange this indicator function so we have this inequality involving these two linear expressions in M. And after some rearrangement, then we get that the payoff can be written as indicator function of this martingale being less than a certain constant x, and x is given by a combination of the strike and the A and the B coefficients. For simplicity, we'll assume that the strike lies in between these ratios. This just ensures that the payoff will be non-trivial. If the strike is less than those two numbers, then we get zero payoff automatically, and if the strike is greater than those two numbers, then we get some definite payoff automatically. But if it's in between, then the problem is truly optional. So now we put in the expression for M. So M is this exponential martingale. So after some rearrangement, we find that this condition is satisfied if we let Z be the normalized, normally distributed random variable obtainable from integral of sigma dw. Then we get expression that is reminiscent of the sort of term that we have in the Black-Scholes theory. So here if we write gamma is equal to integral of sigma ds, then the condition is that Z, which is this n01 random variable, is less than log x plus a half gamma divided by the square root of gamma. X, you'll recall, is this number made up of combinations of the A and B and the strike price. So we put all that together, and then the value of the option becomes expectation of A plus B times M being the martingale, plus the indicator function of Z being less than this particular combination of variables. And the M itself can be expressed in terms of Z. And so we're left with doing an integral, which is very similar to that one has in the Black-Scholes theory. And this gives you the formula for the value of a digital put in the rational log normal model. Now this formula is, I think, well known. And you can see here that x, which enters into the expression for the formula in the same place that the forward price enters divided by the strike price in the Black-Scholes theory. So one can use certain intuitions about the behavior of the price with respect to certain variables. So now we turn to calibration. So we can show that if we're given the initial price of discount bonds for all maturities and the initial prices of options for a system of put options with various strikes and maturities, then it's possible to back out A, B, and sigma. And so this can be done as follows. The trick is first to look at the money forward option. So this is not an unusual idea. So by at the money forward, we mean that the strike is set to be the forward price of the bond, which is this combination of P0 big T divided by P0 little t. And you remember in the Black-Scholes theory, you have this term log of the forward price divided by the strike price, which appears over and over again. But if you set the forward price equal to the strike price, then that's log of 1, which is 0. And just the sort of thing happens in the present situation. It's a little bit less obvious. If you take A big T minus K little t, B big T minus K B little t, and with minus sign, we stick in the expressions for the discount bonds. The thing is that using the formula for the state price density, we know that the initial discount curve is equal to A plus B. So you put that expression in, rearrange, and then you find, again, miraculously, that x is equal to 1. So the term involving log of x drops out. And we're left with a value for the digital put option in that case that involves merely A and B and the normal distribution function valued at gamma. So what this means is that we can rearrange and we can solve for gamma in terms of this option price data, which we regard as given, and A and B. So that's the sort of first step. Now we've eliminated gamma. Then when it comes to A and B, well, A plus B is equal to the initial discount curve, so we can eliminate B. And then this allows us to express gamma entirely in terms of A. So what this means then is if we're given option price data for some other fixed strike that's not at the money forward, for some fixed maturity and variable t's, then we can solve for A. So in this way, we can calibrate the model over any fixed time horizon, let's say from 0 up to big T, to the initial yield curve data and at the money forward option data for some little t in that range, and option data for some other strike for all t in that range. Now, of course, you must understand that we're not attempting to see whether rational log normal fits real data. We sort of privately assume that the rational log normal describes the real world, and the question is, if we're given data from the real world, then can we calibrate the parameters of the model to that data? And then the answer turns out to be yes. So this leads us back finally to the market price of risk in the rational log normal model. And you'll recall this formula that I presented earlier, which shows that the rational log normal model has the property that the market price of risk is linear in the short rate, and the coefficients involve the functions a, b, and sigma. So it follows that once the model has been calibrated to market data, then the market price of risk is completely determined as a function of the short rate. So this means that if I wanted to do a simulation, then I fix A, B, and sigma, and I simulate the way the interest rate is going to run in the future, and that immediately tells me how the market price of risk is going to run in the future. So this shows that the rational log normal model provides an example of a model or a family of models for which full recovery is possible in the sense of Ross. And that's to say, from suitable option data, then we can recover the behavior of the model entirely in the p measure. Well, let's kind of put together what we've said. We've looked at three examples. Of course, other examples can be considered Levy models, diffusion models, and so on and so forth. But even from the material that we've looked at here, various conclusions can be reached. First of all, in the example of the geometric Brownian motion model parameterized by lambda, if the payoff of a contingent claim is given by any function of the value of the underlying stock at the expiry of the claim, then the value of the claim doesn't depend on lambda. This, of course, is well known, but somehow it has kind of creeped into the minds of many people in the community, particularly in the practitioner community, I think, to formulate the idea that somehow option prices in general don't depend on market price of risk, or more generally on risk preferences. But this is not true. So in particular, if we introduce a stochastic volatility model, then even if the volatility is driven by the same Brownian motion as the one that's driving the asset, in general, the resulting option price will depend on the value of lambda. And conversely, we have recovery. In other words, given the price of any option, then we can back out the market price of risk. So such models have full recovery. Nevertheless, there are some models in this category, that's to say stochastic volatility models, for which the stochastic volatility is driven by the same Brownian motion as the asset, for which the price doesn't depend on lambda. And amongst these, for example, are models of the local volatility type, or de Peer type models, where the volatility is some suitable function of the asset price itself at time t and maybe time as well. So the fact that such models don't depend on lambda in the resulting option prices, I think sort of had the effect of enhancing further the general view that it wasn't necessary to consider the effect of market price of risk on option prices. But this is only a valid conclusion for certain classes of models, and it's not true in general. So in the case of interest rate theory, we've seen that families of models can be constructed for which the model parameters can be completely determined from initial prices of data. I showed you in the example of the rational log normal model, but loosely speaking, in most models of the potential type, this is true as well. That's to say, the market price of risk will enter into the resulting values of derivatives. So we conclude that the idea of that option prices in any general sense are independent of the market price of risk or independent of the rate of return on the underlying asset. It's not true. For some models, it's true that option prices are independent of the market price of risk, but in general, this is not the case. I'll stop here. Thank you for your attention.